The automotive world often overlooks one of its most critical components, the tire. It is the sole point of contact between a vehicle and the road, a seemingly simple rubber ring whose complex internal engineering dictates performance, safety, and even fuel economy. The margin for error in its design is negligible, as structural compromises directly translate to catastrophic failure or diminished vehicle capability. A tire is not merely a single piece of molded rubber. It is a sophisticated assembly of diverse materials, each serving a specific structural purpose. At its core are the body plies, typically polyester or rayon cords, forming the fundamental carcass. Over these, reinforcing belts, often steel, are laid, providing tread stability. Finally, the tread itself and the sidewalls are molded around this intricate structure. Consider the fundamental difference between radial and bias-ply construction. Bias-ply tires feature cords running diagonally across the tire from bead to bead, crisscrossing to form multiple layers. This design provides robust sidewall strength but generates more heat and can lead to a less stable contact patch at higher speeds. Radial tires, conversely, have plies running perpendicularly to the direction of travel, with stabilizing belts underneath the tread. This allows for independent sidewall flex, enhancing ride comfort and maintaining a larger, more consistent contact patch, directly improving grip and reducing rolling resistance. The rubber compound used for the tread is a primary determinant of a tire's characteristics. Softer compounds offer superior adhesion, crucial for high-performance driving, where maximum friction is prioritized. However, this increased grip often comes at the cost of accelerated wear and reduced longevity. Conversely, harder compounds are formulated for durability and fuel efficiency, sacrificing some ultimate grip for extended service life and lower rolling resistance. Engineers must carefully balance these opposing demands based on the tire's intended application. Tread pattern design is equally critical, directly influencing traction and water evacuation. Deep, circumferential grooves channel water away from the contact patch, mitigating hydroplaning, a significant safety concern in wet conditions. Lateral grooves and sipes, small, intricate cuts within the tread blocks, create additional biting edges, enhancing grip on wet, icy, or loose surfaces. Off-road tires feature larger, more aggressive blocks, designed to dig into loose terrain, sacrificing quietness and fuel efficiency on paved roads for maximum traction elsewhere. The sidewall of a tire, often perceived as a simple support structure, plays a crucial role in handling dynamics and ride comfort. A stiff sidewall, typical in performance tires, offers precise steering response and minimal deflection during cornering, allowing for more direct transmission of steering inputs. However, this rigidity can result in a harsher ride. Taller, more flexible sidewalls, found in touring tires, absorb road imperfections more effectively, prioritizing passenger comfort over aggressive handling. The tire bead assembly forms the critical interface between the tire and the wheel rim. Composed of high-tensile steel wires encased in rubber, the bead ensures an airtight seal and prevents the tire from separating from the rim, especially during high-speed maneuvers or impacts. A compromised bead, through improper mounting or damage, directly jeopardizes air retention and structural integrity, leading to rapid deflation and a loss of vehicle control. Internal reinforcement belts, usually located directly beneath the tread, are integral to a tire's performance and durability. Steel belts provide exceptional puncture resistance and help stabilize the tread, preventing distortion during rotation. This stabilization maintains a consistent contact patch, enhancing high-speed stability and extending tread life. Fabric belts, often nylon, contribute to conformity and temperature resistance, particularly crucial in tires designed for extremely high speeds. Heat buildup within a tire is an engineering challenge with direct safety implications. As a tire rolls and flexes, internal friction generates heat. Excessive heat can degrade rubber compounds, reduce inflation pressure, and ultimately lead to tread separation or a blowout. Tire design incorporates specific materials and structural elements, such as heat-resistant compounds and optimized ply layouts, to dissipate heat efficiently, especially under heavy loads or sustained high speeds. Rolling resistance, the force opposing a tire's motion, directly impacts fuel efficiency. This resistance primarily stems from the deformation of the tire as it rotates, along with internal friction and air resistance. Tire manufacturers employ specific tread patterns, lighter internal materials, and optimized rubber compounds to minimize rolling resistance. A reduction in this force translates into less engine power required to maintain speed, directly lowering fuel consumption. Load index and speed rating are critical safety parameters mandated on every tire. The load index specifies the maximum weight a tire can safely support, while the speed rating indicates the maximum speed at which the tire can carry its rated load under specified conditions. Exceeding either of these limits places undue stress on the tire's structure, increasing the risk of premature failure and loss of control, compromising vehicle safety. Tire pressure, though often overlooked, is the single most important factor influencing a tire's performance, safety, and longevity. Underinflation causes excessive sidewall flexing, generating heat, increasing rolling resistance, and accelerating wear on the outer edges of the tread. Overinflation reduces the contact patch, leading to decreased grip, a harsher ride, and accelerated wear on the center of the tread. Maintaining correct pressure is non-negotiable for optimal vehicle dynamics and structural integrity. Wheel balancing and alignment are essential maintenance procedures that directly impact tire performance and vehicle operation. Imbalanced wheels cause vibrations, leading to uneven tire wear, reduced ride comfort, and stress on suspension components. Incorrect wheel alignment, where the angles of the wheels are not set to manufacturer specifications, results in premature and uneven tire wear, pulling of the vehicle, and compromised handling, demanding more frequent tire replacement. Ultimately, tire design involves a series of calculated compromises. A tire optimized for maximum dry grip will not excel in snow or rain. A tire built for extreme off-road durability will be noisy and inefficient on pavement. Engineers must meticulously balance performance, safety, and efficiency against specific use cases, resulting in a vast array of specialized tires, each tailored to a particular set of demands and driving conditions. Understanding these underlying principles of tire construction and design empowers drivers to make informed decisions. Recognizing the interplay between plies, compounds, and patterns reveals why selecting the correct tire for a vehicle's intended purpose and operating conditions is not merely a preference, but a critical factor in maximizing a vehicle's performance, ensuring occupant safety, and optimizing fuel efficiency over its operational lifespan.